Good evening, sir. Uh, today I'll be Good evening, sir. Today I'll be talking about blockchain technologies, and the topic that I'll be talking about is building a Merkle tree. The subparts that we'll be covering in this particular video will be introduction to Merkle tree, how Merkle trees work in blockchain, application of Merkle trees, limitations of Merkle trees, future developments, and finally conclusion, which will include importance of Merkle trees. So let's start with the basic introduction. Merkle trees are a fundamental concept in blockchain that enable efficient and secure verification of transactions. A Merkle tree is basically a data structure that allows for the creation of summary or hash of all transactions in a block. This hash can then be used to verify the integrity of the transaction without needing to examine each one of them individually. A Merkle tree, also known as a binary hash tree, is basically, as we said earlier, it is mainly used for verifying the integrity of the large sets of data. Merkle trees usually are binary trees which contain cryptographic hashes. The term tree is used in computer science to describe a branching data structure, but these trees are usually displayed upside down with the root at the top and the leaves at the bottom of a diagram, as we'll see in the examples that follow. The use of Merkle trees in blockchain has several benefits. It enables faster verification of transactions, as only the root hash needs to be checked instead of every transaction. So basically, we'll be just checking the root node of the Merkle tree to verify all the transactions that follow, and we need not verify all the transactions, as in all the leaf nodes and all the internal nodes that are there in the Merkle tree. It will also enhance the security by making it more difficult for attackers or hackers to tamper with the transaction, as any changes that are made to transaction would result in a different hash value. So if some attacker or some hacker tries to attack or tamper any of the transaction that is already existing, then he need to change all the hash values that are there in the Merkle tree, which will be a long and difficult process. The cryptographic hash algorithm used in Bitcoin's Merkle trees is SHA-256 applied twice, also known as double SHA-256. Uh, when n data elements are hashed and summarized in Merkle tree, we can check to see if any one data element is included in the tree with at most 2 into log 2n calculations, making this a very efficient data structure. Uh, Merkle trees are basically constructed in a bottom-up approach. In the example below, we'll be seeing how to build a Merkle tree. So basically, we'll start with four transactions, as we can see, which are A, B, C, D, and then the transactions are not stored in the Merkle tree. Rather, the data is hashed, and the resulting hash is stored in each of the leaf node as HA, HB, HC, and HD respectively. So HA will be equal to SHA-256, which is transaction A. So as we can see here, we have stored um, H of A, H of B, H of C, and H of D. So in all of the H of A will have transaction A, H of B will have the hash of transaction B, and similarly for C and D. Uh, Now consecutive pair of leaf nodes are then summarized in a parent node by concatenating the two hashes and hashing them together. For example, to construct parent node HB, the two 32-bit hashes of the children are concatenated to a 64-byte string. That string is then double hashed to produce the parent node's hash H of AB, which is equal to SHA of 256, which is basically the addition concatenation of H of A plus H of B. This process will continue until there is only one node at the top, and this node is known as the Merkle root. That 32-bit hash is stored in the block header. Uh, so as we can see here, we have four initial transactions, h of hashes of the transaction, h of A, h of B, h of C, and h of D. We'll concatenate these, which will form the parent nodes, and later we'll concatenate these parent nodes to form the final root node. Uh, since the Merkle tree in this example is a binary tree, it needs an even number of leaf nodes, and suppose if there is an odd number of transactions to summarize, the last transaction's hash will be duplicated to create an even number of leaf nodes. So this is how we'll make a balanced tree. So let's say if we had only three transaction, so we would create the hash value for transaction A, hash for transaction B, and hash for transaction C. And then instead of, let's say if we don't have a transaction D, then we'll just duplicate the transaction C, the hash value for transaction C, and then concatenate for loop. So similarly, as we can see here, there are multiple hash values that we have taken, and then we are concatenating it to make a final root node, which is known as the Merkle root. Uh, so irrespective of how many of our hashes we are taking, we'll be summarizing the final root into a 32-byte format. So now we'll see how Merkle trees work in blockchain. Merkle trees basically work by recursively hashing pairs of transactions until a single hash value known as the root hash is produced. Each pair of the transaction is combined into a single hash value as we have seen previously, which is then paired with another hash value and hashed again. This process continues until there is only one hash value remaining, which represents the root of the tree. Uh, Similarly, when a new block is added to the blockchain, its transactions are added to the Merkle tree and root hash is included in the block header. When a node on the network receives a new block, it can quickly verify the integrity of the transaction by checking the root hash against the one stored in the previous block header. If the hashes match, then the transactions are considered valid. So here we'll be basically checking the hash value of the new transaction with the transactions that are already existing, and then only if the condition is satisfied, only then we'll add this new transactions hash value into the Merkle tree. So this is the code below that demonstrates the creation of a Merkle tree. The leaf nodes hashes up to the root. So we'll be using the libBitcoin library for executing and building this particular code. So in the first line of the code, we can see we are just checking if the hash list is empty. Uh, then we are checking if there is more than one hash in the list. If it is there, then it will keep looping. We then in the while loop itself, we will be using a if statement to check whether the number of nodes are even or not. If the number of nodes are not even, then we have to duplicate the last hash value. Then we'll be checking the new hash list. We'll be creating a new hash list. In the new hash list, we'll be basically concatenating the previous two hash values to make a parent node, and this process will continue until a parent we have a final um, Merkle root. Uh, in the above program, the create Merkle function takes a list of transaction hashes as an input and returns a Merkle root hash. It works by repeatedly concatenating pairs of hashes in the list, hashing the concatenated value, and adding the resulting hash to a new list. This process is repeated until one hash remains, which is the Merkle root hash. The main function creates a list of transaction hashes and passes it to the create Merkle function to generate the root hash. The resulting hash is printed to the console. So here we can see that we have basically compiled the program, and then we can see that we have got the current Merkle hash list and the final Merkle root hash value. Now Merkle tree efficiency. The efficiency of Merkle tree becomes obvious as the scale increases. For example, proving that a transaction is part of block, it requires, let's say, we have a table here that demonstrates the Merkle tree efficiency. Let's say we have the number of transactions are 60. The approximate size of the block is 4 kilobytes. The number of hashes will be 4 hashes, which is also the called the path size, and the path size in bytes will be 128 bytes. Similarly, for like 65,535 transaction, the approximate size of the block will be 16 megabytes, which will require 16 hashes, and it will be 512 bytes. From the above table, we can see that the block size increases rapidly from 4 kilobytes with 16 transactions to a block size of 16 MB to fit 65,535 transactions. The Merkle tree path required to prove the inclusion of a transaction increases much more slowly from 128 bytes to only 512 bytes. With Merkle trees, a node can download just the block headers, which is 80 bytes per block, and still be able to identify a transaction's inclusion in a block by retrieving a small Merkle path from a full node without actually storing or transmitting the vast majority of the blockchain, which may be several gigabytes in size. Nodes which do not maintain a full blockchain are basically called simplified payment verification or SPV nodes. These use Merkle paths to verify transactions without downloading full blocks. So, by not using the full blocks, we are saving on a lot of storage space, and this also makes the layout of the entire Merkle tree and all the transactions very simple. Now let us look at the applications of Merkle trees and blockchain. Merkle trees have several applications in blockchain beyond transaction verification. They can also be used for efficient storage and retrieval of data, as well as for proof of existence and proof of ownership systems. For example, a decentralized file storage system could use Merkle trees to store and retrieve files by their hash values. Another application of Merkle trees is in the implementation of smart contracts. Smart contracts often involve complex logic and multiple transactions, which can be difficult to verify efficiently. By using Merkle trees, the validity of a smart contract can be quickly verified by checking the root hash against the one stored in the blockchain. Now we'll see about Merkle trees and simplified payment verification. Merkle trees are used extensively by simplified payment verification nodes, as we had seen in the previous slides. SPV nodes don't have all transactions and do not download full blocks, just block headers. In order to verify that a transaction is included in a block without having to download all the transactions in the block, they use an authentication path or Merkle path. Consider, for example, an SPV node that is interested in incoming payments to an address contained in its wallet. The SPV node will establish a Bloom filter on its connections to peers to limit the transactions received to only those containing addresses of interest. When a peer sees a transaction that matches the Bloom filter, it will send that block using a Merkle block message. The Merkle block message contains the block header as well as the Merkle path that links the transactions of interest to the Merkle root in the block. The SPV node can use this Merkle path to connect the transaction to the block and verify that the transaction is included in the block. The SPV node also uses the block header to link the block to rest of the blockchain. The combination of these two links between the transaction and the block in which the hash value of the transaction is stored, and between the block and the blockchain, proves that the transaction is recovered in the blockchain. All in all, the SPV node will have received less than a kilobyte of data for the block header and the Merkle path, an amount of data that is more than 1,000 times less than a full block, about 1 megabyte, which is happening currently. Now let us look at the limitations of Merkle trees and blockchain. While Merkle trees offer many benefits in blockchain, they are without they are not without any limitations. Like every good algorithm or data structure will always have some limitations. So the first limitation is the potential for collision attacks. In this, basically, when two different sets of transactions produce the same hash value, while this happening is very rare, it can potentially allow for fraudulent transactions to be included in the blockchain. Another limitation is the need for all transactions to be processed in batches of two. This can lead to inefficiencies when dealing with large number of transactions, as some transactions may be unpaired and require additional processing time. Uh, Let us look at the future developments in Merkle trees for blockchain. Despite the limitations that we saw in the previous slide, Merkle trees continue to be an important concept in blockchain technology. Researchers are currently exploring new ways to improve the efficiency and security of Merkle trees, such as through the use of alternative hashing algorithms or the development of new data structures. One promising area of research is the use of recursive Z-case snarks, which basically stands for zero-knowledge succinct non-interactive arguments of knowledge, to further enhance the privacy and scalability of blockchain. These techniques could enable the verification of entire blocks without needing to reveal any information about the individual transactions. Finally, uh, I'd like to conclude this particular slide PPT with the importance of Merkle trees in blockchain. So basically, in conclusion, Merkle trees are a critical component of blockchain technology that enable efficient and secure verification of transactions. They offer several benefits, including faster verification and enhanced security, and have numerous applications beyond transaction verifications, which we saw in the previous slides. While there are limitations to Merkle trees, ongoing research is exploring new ways to improve their efficiency and security. And as blockchain continues to evolve and mature, Merkle trees will undoubtedly remain an important concept in the field of blockchain. Thank you so much, sir.